So good evening, everyone. Let us continue our discussion. So today we will be discussing basically the course content for the ninth week. So initially we will be going through briefly going through the deflection of RC beams, and thereafter we will go through the design of footings. Okay. So yeah, so let us start then the discussion. So why why the deflection in RC beams is an important parameter? So that is because uh, there is various difficulties arising in the flexure member. Okay, so firstly, what happens is there is variation in flexural stiffness along the span owing to the uncertain nature and extent of cracking. Okay, so that leads to deflection. And secondly, there is variation in shrinkage and creep owing to the curing condition, humidity, exposure, composition of concrete, age at loading, etc. Okay. So because of these reasons, there are chances of deflection that which can arise, and there is substantial amount of deflection. So that's why it is an important criteria for checking. Okay. So that's why in limit state uh, there is a criteria for deflection also in the serviceability part. Okay. So yeah, so along with cracking, there is a criteria for the deflection, limit state of deflection. So yeah, so basically, if we assume this beam to be simply supported, so we will find that the maximum central deflection occurring is 5384 WL to the power 4 by EI. So this you will get from the mechanics class. Okay, so from if you have I'm sure you have gone through the mechanics course. So from there you will know how it is calculated. Okay, and even from the structure analysis course also you will have an idea. Okay? So yeah, so if we see this, the delta, that is 5 by 384 WL to the power 4 by EI for the UDL case in a simply supported beam. So here if you see here, then this 5 by 384 WL to the power 4, so that is basically can be written as F, which is basically the load span arrangement. So that means it basically depends on the span as well as the arrangement of the loading. Okay, so it is mainly in this case it is 4 times 4 to the power 4 times proportional to the length, and the linearly proportional to the load. Okay, UDL. Similarly, if we take the example of uniformly loaded by moment, okay, in simply supported beam case, so here you will see again that delta max value is ml square by 8EI, okay. So that means 1 by 8 value is 0.125, okay, which is basically the beta value, okay. And so you can write that it is beta psi L square, okay. So this beta value is basically 0.125, okay, and psi is basically the m by EI value. Please mute yourself. Thank you. So yeah, so beta value is here 0.125, and psi value is curvature. Okay, that is m by EI. So yeah, so if we see here, the beta value is 0.125 and xi value is curvature, which is m by EI. Okay, and the L square is the length, right? So we can write it as beta xi L square. Okay, so now let us see how to calculate the deflection. Okay, so basically for calculating the deflection, we basically follow the annexure C, okay, of the IS 456 2000, which is present in page 88. Okay, so for the calculation of deflection, we basically use the effective moment of inertia. Okay, so how to calculate this? So this is basically calculated using this formula. Okay, so I effective is equal to IR by 1.2 minus MR by M into Z by D into 1 minus X by D into BW by B. Okay, so in this case IR is equal to second moment of area of the crack section. Okay, MR is basically the cracking moment, which is equal to FCR. Okay, into IZR by a YT. Okay, so we'll see what are these terms. FCR basically is the modulus of rupture. Okay, so that is the flexural strength. So this is zero point 0.7 root FCK, and it is calculated. This formula we have obtained from clause 6.2.2, page 16. Okay, from the same IS 456. Similarly, IGR is the gross second moment of area, okay, and YT is the distance from centroidal axis of gross section, okay. So that is basically this value, okay, this distance. So yeah, so X is basically the neutral axis depth, okay. Z is basically the lever arm, okay. M is maximum moment under service loads, okay. And this condition has to be satisfied. That is, your second moment of area of the crack section should be either less than equal to the effective moment of inertia, and that should always be less than the gross moment of inertia, okay. So to understand it completely, let us take the example, okay. So say for example, this is a T beam given, okay, which is having a grade of concrete of M20, steel of Fe415 grade, span is of 7.5 meter. It is simply supported. The dead load is 15 kilonewton per meter and live load is 10 kilonewton per meter, okay. And the flange depth is 125 millimeter, okay. Depth of web is 575 mm, and there are three 25 dia bars in the tension zone, okay. So and the width of flange is your 2200 millimeter, okay. So how how we will proceed to calculate the deflection, okay. So yeah, so first we'll calculate the D value effective depth, which is basically 700 minus 25, which is basically the clear cover, okay, and minus 25 by 2, okay. So that is the half of diameter, okay. So that is basically equal to 662.5 millimeter, and the area of steel is 3 into pi by 4 into 25 square, which is 3 into 491, that is 1473 millimeter square, okay. And moment, because it is simply supported, so the maximum moment will be WL square by 8, right? That is again we obtained from the structure analysis course, okay. So M is equal to WL square by 8. W is the summation of dead load plus live load. So dead load is 15, live load is 10, right? So it is 15 plus 10 into 7.5 square, which is the span, divided by 8, okay. So that comes to be comes out to be 175.78 kilonewton meter, okay. So similarly, from IS code, we know the EC value, that is the elastic short-term elastic modulus. So that is equal to 5000 square root of FCK, right? And FCK value here given is 20, right? So it is 5000 into square root of 20, which is basically 22,361 Newton per millimeter square. Okay. Um, Now we will see find the modular ratio value M, okay. So that is basically ratio of elastic modulus of steel and concrete. So that is basically 2 lakh by 22,361, right? So that is 8.94, okay. And FCR value comes to be zero point 0.7 into square root of 20, which is 3.13 megapascal, right? So assuming now we'll find the this one, the depth of neutral axis, okay. So let us first assume that it is belongs to the first case, that is it is inside the depth of flange, okay. So flange depth is how much? 125 mm, right? Yeah. So we will assume that it is less than 125, okay. So we can directly use the simple equation, okay. So we will just by computing the comparing the forces, okay, tensile and compression. So in the transform section we get how much, so equating half bx square equal to m ast into d minus x. So from this we will calculate the x value substituting other values, right? So calculating all the like substituting the values and calculating the value of x, we get it to be 83.27 millimeter, right? And this is obviously less than 125 millimeter, so our assumption is right. That is, the depth of the neutral axis is inside the flange, right? So after getting this, we will calculate the lever arm, okay. So lever arm basically is z, okay, that is d minus x by 3. So that comes out to be 634.75 millimeters, okay. Now we will calculate the IR value, okay. So that is the second moment of area of crack section, okay. So for that, yeah, so that will be calculated using this formula. So this formula comes basically from the this one, the first part, that is the moment of inertia of the concrete part, okay. So that is equal to bd cube by 3, bh cube by 3. So that is with respect to the base, because we will calculate from the base, which is the neutral axis, right? Otherwise, if it would have been in the from the middle of the section, it would have been bh cube by 12. Okay, now using parallel axis theorem, if we can see, so you must have done this in mechanics course. So it comes out to be bh cube by 3 in case of rectangle, right? So this is the case, so it is bx cube by 3. And this is the part, this is the part for the steel. Okay, so this MAST is the equivalence of concrete, okay, in terms of steel. And d minus x whole square is the this distance, right? So that is the your total moment of like second moment of area of crack section, okay, of the whole part, right? So that is basically the core, this one. Here also we have basically applied the parallel axis theorem only. So this is uh, for this is bx cube by 3 for the concrete, and this is basically ax square only. So parallel axis theorem, so this is the distance square of distance, and this is basically the area of concrete in equivalent area of concrete in terms of steel, right? So substituting all these values, we get the IR value to be 4.8414 into 10 to the power 9 millimeter to the power 4, okay, which is the second moment of area of the crack section. Okay. Now we shall calculate the distance of centroid from tension fiber. Okay. So for this, the Y2 value, it will come to be 250 into 700 into 700 by 2 plus 2200 minus 250 into 125 into 575 plus half of 125, right, divided by the whole area, that is 250 into 700 plus 2200 minus 250 into 125, right? So using this, we will get the distance of centroid from tension fiber, which comes to be 517 millimeters, right? So this is the Y2 value. And then we can calculate the gross moment of inertia. Okay, so that is basically nothing but the total moment of inertia. Okay, so that is simply the total gross area minus this these two portions. Okay, so that is 250 into 517 cube. Okay, the Y2 YT value divided by 3 plus 2200 into 700 minus 517. So this whole area, okay, whole cube by 3, okay, minus these two portions. Okay, so that is 2200 minus 250, okay, into 700 minus 517 minus this 125 whole cube, okay, divided by 3. Okay, so this is a neutral axis. So about this, the gross moment of inertia we will calculate. Okay, so that comes to be 1.588238 into 10 to the power 4 millimeter to the power 4, right? So the MR value, which is the cracking moment, that will be equal to IGR by YT into FCR. So these all values we will find in the annexure C of IS 456. Okay, so this MR cracking moment, it is IGR by YT into FCR, which is 1.588238 into 10 to the power 10 into 3.13 by 517 into 10 to the power 6 kilonewton meter, and that comes out to be 96.15 kilonewton meter. Okay, so this using like finding all these values, we just substitute it into the required variables. Okay, and by this we can calculate the I effective. Okay, so initially we find this value 1.2 minus mr by m into z by d into 1 minus x by d into bw by b, right? So substituting these values, we get this denominator value as 1.148. Okay, and ir value, we will see. So I effective value basically will be 1 by 1.148 into IR, that is 0.871 IR. Okay, but according to this condition, okay, I effective value can't be less than IR. It has to be either equal or greater. Okay, and it has to be less than IGR. Okay, so it is less than IGR, but it can be less than IR. So therefore I effective has to be equal to IR. Okay, so therefore, yeah, so that is the basically this one. So IR value is how much? 4.8414 into 10 to the power 9 millimeter to the power 4, right? So the I effective value will be also the same value as the IR value. Okay, now, so therefore let us see what is the deflection value, okay, due to the dead load, right? So deflection due to dead load is delta DL, which is 5 by 384 into 50 into 75, 15 into 7500 to the power 4 by 22,361 into 4.8414 into 10 to the power 9, that comes to be 5.7, comes out to be 5.7 millimeter. Okay, And the delta deflection for live load, that again comes to be 5 by 384 into 10 into 7500 to the power 4 divided by 22,361 into 4.8414 into 10 to the power 9, that is 3.8 millimeters, right? So yeah, so that is the this one, the value due to deflection due to dead load and live load. Okay, and for the case of this one, the deflection due to the shrinkage. Okay, so we can find the delta cs value using clause c3. Okay, page 80 is 456, that is k3 psi cs l square. Okay, so this is basically the deflection due to dead load and live load, and this is basically the deflection due to the shrinkage. Okay, so this k3 value, it is a coefficient, and it varies for various types of supports. Okay, for cantilever, the k3 value is 0.5. For simply supported, it is 0.125. For members continuous at one end, it is 0.086, and for fully continuous members it is 0.063. Okay, so the size cs, that is the shrinkage curvature, that is equal to k4 epsilon cs by capital D. Okay, so this epsilon cs value is constant, it is 0.0003. Okay, and K4 value is basically your this as per the IS code and exergy, it is 0.72 into PT minus PC by square root PT. Uh, if if PT minus PC is between 0.25 to 1, okay, so we have to use K4 equation. We have to use this equation for the value of K4, and that has to be less than equal to 1. Okay, and if PT minus PC value is greater than equal to 1, then we have to use this equation, which is 0.65 PT minus PC by square root of PT, and this value also has to be less than equal to 1. Okay, so therefore the PT value can be calculated as 1473 into 100 by 250 into 662.5. Okay, that is tensile reinforcement percent. So that is 0.889 in this question. Okay, and here PC, there is no PC because no compression reinforcement, so that is 0. Okay, and therefore PT minus PC, right? So that is 0.889, which is between 0.25 and 1, right? So therefore we will be using this formula for calculating the K4. Okay, so the K4 value will be equal to 0.72 into 0.889 minus 0, okay, by square root of 0.889, right? And that comes out to be how much? 0.6788, right? K4 comes out to be 0.6788, right? So as I told you, the W epsilon CS value is 0.0003. It is fixed, and capital D 700 mm and K4 is 0.6788, right? So epsilon xi CS value comes to be K4 epsilon CS by D, that is 2.9091429 into 10 to the power minus 7. Okay, so that is the value we obtain, and using this value we can calculate the delta CS value, which is K3 xi CS L square. K3 in this case, that is simply supported, it is 0.125. Okay, this value, so it is 0.125 into JICS, which is 2.9091429 into 10 to the power minus 7 into L square. L is 7.5, right? Yeah, so L is 7.5, so it is 7,500 square. Okay, so that comes to be 2.04 millimeters. Okay, so that is the deflection value due to shrinkage strain. Okay, so that is shrinkage, and one more deflection is there, that is the deflection due to creep. Okay, so that is shrinkage, that is mainly shrinkage mainly occurs due to the evaporation of water, okay, inside the concrete. Okay, concrete pores. And creep mainly that is the long term deflection, okay, after the instantaneous deflection, okay, which occurs, and it is reduced in nature. Okay, so it reduces with time. Okay, so that is long term deflection basically. So this for finding this, so we can use page 89. Okay, we can refer C4 clause, page 89, IS 456. So here we will be using ECC value, that is the long term modulus of elasticity. Okay, so EC is the basically short term modulus of elasticity, which is 5000 square root FCK. Okay, but for finding the long term, we have to divide EC value by 1 plus theta, and theta is basically the creep coefficient. Okay, and it is always taken to be 1.5. Okay, so the permanent deflection due to creep. Okay, so that is equal to F by ECC into I effective minus F by EC into I effective. So this formula is given in annexure C4, annexure C clause C4, page 89, IS 456. Okay, so solving this we get F this comes to be F by I effective into 1 plus theta by EC into minus 1 by EC. So I ECC is equal to EC by 1 plus theta, right? So it comes like this, and taking out the EC value, we get F by EC into I effective into 1 plus theta minus 1. So plus 1 minus 1 cancel. So it becomes F by EC into I effective into theta. Okay. So now F by EC I effective is nothing but delta DL, dead load deflection, and theta is the creep coefficient, which is 1.5. Okay. So the this one, the creep deflection basically will be 1.5 times delta DL, that is 1.5 times 5.7, which is 8.55 millimeter. Okay, so therefore the total deflection basically will be the summation of all, that is the deflection due to summation of the deflection due to dead load plus live load plus shrinkage and plus creep. Okay, so this comes out to be 5.7 plus 3.8 plus 2.04 plus 8.55, that comes to be that comes out to be 20.09 millimeter. So, okay, so this value has to be less than the L by 350, right? So it should be less than L by 350 value. Okay, so that is the deflection limit. Okay, so if that is less, so we can say that the deflection criteria has been checked for the flexural member. Okay, so that is how we have to check for we have to check the deflection clause for the flexural members or the RC beams. Okay, so now let us go to the design of footings. Okay, so yeah, so if we see this case, okay, so few terms there will be such as the soil bearing capacity or the soil safe bearing capacity, okay, which is SBC. Okay, so that is equal to P by A, that is load acting on the footing from the column divided by the area, right? So that is basically the using this you in case of footings, the load divided by the area where the soil is acting, you will get the safe bearing capacity of soil. Okay, so there will be some permissible limit, and we have to see that it is always less than that. And as like earlier classes we discussed, so this is the beam bearing capacity. Okay, so it can be in 5 kilonewton per meter square, 10 kilonewton per meter square. So this is the basically for the tile beam. Okay, that is the primary, the beam which is in the uh, which is in the initial after just after the plinth. Okay, so the plinth beam is basically called the tie beam. Okay, the initial beam. Okay, from the foundation. Okay, after the foundation which has been constructed. Okay, so there is an initial beam, so that is the tie beam. Okay, or it is also called as splint beam. And here they have used 5 kilonewton per meter square, 10 kilonewton per meter square. In the safe bearing capacity, it can be in tons. Okay, so it can take various various units. We know 1 ton is equal to 1000 kg, like that. So yeah, so there are various types of footing. Okay, so there is isolated footing, combined footing, footing on piles. Okay, and inside isolated footing also there is square footing, rectangle footing, right? So there are various types of footing. So if you yeah, so if you want to learn more on footing, you can also take geotechnical courses. Okay, so they are mainly, they are mainly designed for that. Okay, the courses are mainly designed for this type of subjects. We are basically going to see how to design. Okay, mainly from the design aspect, we will address the course on footing. Okay, so what is basically the area of footing? So that is the amount, the area we will require for the footing. That will be nothing but the service load acting on the column or the design load acting on the column divided by the safe bearing capacity of the soil below, right? So that's why the SBC value is important. And the factored load to this factored load is needed for the checking the thickness of footing also. Okay, one is the area of footing and second is the thickness of footing. And this footing can be of various types. Okay, so it can be uniform. Okay, that is it is like a prism. Okay, it can be sloping. Okay, and it can be of some irregular shape also in between. Okay, so yeah, so if there is a load as well as a moment, that is some eccentric load is acting, so the the load, that the load density which will occur, it is equal to P by BL in plus minus 6m by BL square. Okay, so this equation basically, this for how it has come, so we don't need. So this is mainly from geotechnical, so you can check that out. I think from some Tarjagi equation and Coulomb equation and all those. So we don't require all those. Just for like having a brief understanding, I have shown here. So if we see that the force in this side, so it will be higher. So it will be P by BL plus 6m by BL square. Why? Because the load as well as the moment all are acting in the same direction. Okay, but if we see this in this part, it will be lesser. This in this case it is P by BL. Okay, here if we go to the right side, it will be increasing, that is plus 6m by BL square, and if we go to the left side, it is decreasing, that is minus 6m by BL square. Why? Because in the left side, the load acting will axial load acting will be in the downward direction, but the moment, okay, moment here it will be acting in a downward direction because it is anti-clockwise, right? So it will act at the downward direction, but in this case, in this side, it will be acting in a upward direction. Okay, like this, it will be like this, right? Like this. So this and this, they are counteracting each other, so it will be in minus. Okay, so if we can balance that out, we can find a region also where it will be zero. Okay, so like this it occurs, and this is the dimension of the section, okay, of the footing. So moment of inertia is BL cube by 12, as I told you. uh, through if the section is if the axis is from the between, okay, from the middle, and Z is the elastic section modulus. Okay, so I think you must have you must know what is this. So this comes from the solid mechanics courses. Okay, so Z is equal to nothing but this one, I by Y. Okay, so Y in this case is L by 2. Okay, and that is basically the depth from the central axis, neutral axis. So I by L Y, that is Y is L by 2. So I by L by 2 is nothing but BL square by 6 for the elastic section modulus. Okay, so yeah, so why the thickness of how much thickness of footing is required basically, that we need to know. Okay, so how much thickness of footing is required? Okay, so firstly it should be sufficient to resist the shear force, okay, without shear steel. So that much requirement is there, that it should be able to resist the shear force without any requirement of shear steel. Okay, and basically we assume the shear strength of concrete to be around 0.35 newton per millimeter square. Okay, for a grade of M20. So that can be checked in the IS code itself. I think it was stable 19, and it should be, the thickness should be sufficient to resist the bending moment without compression steel. Okay, and thirdly, it should be able to withstand corrosion that can be caused from ground. So the thickness of the footing should be considered based on that it should be able to resist shear force without any shear steel. It should be able to resist the bending moment without any compression steel, and it should be able to withstand corrosion that can be caused from the ground. Okay, so as per the clause 26.5.2.1, okay, the minimum percentage of steel is 0.15% for Fe250, that is mild steel, and 0.12% for Fe415, that is high yield strength deformed steel, okay, HYSD. And the clear cover, okay, basically from the steel that is required, okay, it is such that it should not be less than 40 millimeter, that is uh, that is the minimum value, but it should in case of lean concrete it should be 50 millimeter as well, and in case of if the footing is directly on the ground, it should be as high as 75 millimeter. Okay, so those are some of the criterias. Okay, so it is better to go for a higher value. Okay, so it should never be less than 40 millimeter. If it is lean concrete, it should be 50 millimeter, and if it is directly placed on ground, it should be even higher, that is about 75 millimeter. Okay, so basically for the design of footing, we basically consider three critical sections. Okay, so two section comes from shear and one section comes from bending. Okay, so like there is three conditions for critical section. Okay, one is one-way shear, one is two-way shear, and one is bending. Okay, so say for example, if we take the case of bending, so bending, the critical section always occurs at the face of the column. So this is the column, this is the footing, okay. This is the footing of dimension b by l, and this is a column basically, which is having a dimension of a by a. That is a square column, right? So here, the critical section in case of bending is directly at the face of the column, okay. And if we want to find the bending moment, it comes to be half qb into l minus a by 2 whole square. So this is, I have dissected the parts like the calculation. I have broadened the calculation how it comes, okay. So basically we take this load, okay, because this load will be trying to trying to bend it, right? It will be acting as a overturn. It will try to overturn it. So it is the bending moment, okay, from this region, okay. So this comes to be q into b into l minus a by 2 into half into l minus a by 2, okay. And yeah, so that is the case in the case of bending, okay. So bending, the critical section is always occurring at the column face, okay. However, in case of shear, there are two cases: one-way shear and two-way shear. Two-way shear is also called as punching shear. Here, the critical section is little different. Okay, so in bending, it was directly at the face of the column, but in shear, for the one-way shear case, the critical section is at a distance of d. Okay, that is the depth of the footing from the column. Okay, so the critical section occurs at a distance which is equal to the depth of the footing from the face of the column, that is d, okay. That is for the one-way shear. And in case of two-way shear, which is also called as punching shear, here the distance is half of d, okay, that is d by 2, okay. So here the critical section occurs, okay, this is the critical section, okay. So this is occurring at a distance d by 2, okay, from the face of the column, okay, where d is the depth of the footing, okay, effective depth of the footing, okay. So if you see in this case, two-way punching shear, a is equal to the column size, okay. Say a is equal to column size, and we have considered a square column. So the perimeter will be, for the critical section, the perimeter will be 4 times a plus d by 2 plus d by 2. So because it is a square, okay, so this will also be a square, the critical section. So it will have a distance of how much? A plus d by 2 plus d by 2, right? A plus d by 2 plus d by 2, and that is 4 times, okay. That is a perimeter. So it is 4 into a plus d by 2 plus d by 2, okay. So that comes to be 4 into a plus d, okay, and that is the perimeter of the critical section. And in this section, the shear force that will be acting will be basically what? The perimeter into the depth, okay, and into the allowable punching shear stress, okay. So that is the shear force or the shear strength, okay. So the shear strength will be basically 4 into a plus d into d into gamma p, okay. So where or tau p, which is the allowable punching shear stress, okay. So we will understand more when we solve one example, exemplar example. So the minimum depth of the footing, okay, that should be such that the depth should be safe in one-way and two-way shear without shear reinforcement, okay. The depth should be safe for the bending moment without compression reinforcement, okay. And it should be at least 150 millimeter minimum, and it should have a reinforcement of 0.15% for mild steel and 0.12% for HYSD steel, okay. So depth basically criteria is without shear reinforcement, it should be able for it should be safe for one-way and two-way shear. Without compression reinforcement, it should be safe for bending moment, and it should have a minimum value of 150 millimeter, and it should be it should have a tensile reinforcement of 0.15% for mild steel and 0.12% for HYSD steel, okay. So basically, as we just discussed, there are three critical sections: one for bending moment and two from shear force. So for the bending moment, the critical section is directly at the face of the column, like in this section only, okay. For one-way shear, it is at a distance d, that is the effective depth of footing from the column face. And for the two-way shear case, it is at a distance of half of d, okay. That is half of effective depth of footing from the face of column, in the middle, okay. So that those are the points we have to keep in mind, okay. So now let us try to understand this criteria using by solving a problem. Okay. So let us design a square footing. Okay. For a which is subjected basically to a dead load of 1100 kilonewton. Okay. Imposed load of 500 kilonewton, and the column is of square dimension, that is 450 by 450 millimeter. Okay. And it is having a tensile reinforcement of 25 dia bars. Okay. And the concrete is of grade M20 and steel is of grade Fe415, and the safe bearing capacity is 200 kilonewton per meter square. Okay. And let us assume the self weight of footing is 100 kilonewton. Okay. So initially, if we see what is the load, that is a total load that will be acting in the, like, that will be acting in the soil, it will be dead load plus live load plus weight of footing, right? So it is 1100 plus 500 plus 100, which is equal to 1700 kilonewton. Okay. So that is the load, total load that is acting. And the area of footing basically that will be equal to 1700 by 200. Okay. So because 200 is a safe bearing capacity, right? So it is 1700 by 200, which is equal to 8.5 meter square. Okay. And as it is a square footing, finding the square root, we will get the size of the required size of footing. Okay. So square root of 8.5 is 2.915. So 2.195 by 2.195 meters is the required dimension of the footing. Okay. Required footing. So making it rounding it, so basically we're taking a higher version, we get, let us take 3 meter by 3 meter. Okay. So we will adopt a size of footing having dimensions of 3000 millimeter by 3000 millimeter. Okay. So now let us check the check at the critical sections. Okay. For one-way shear, two-way shear, and bending moment. Okay. So for M20, the minimum shear stress is 0.35 Newton per mm square. That is shear strength of concrete, right? So the Q, that is load acting, it is P by L square. Okay. So the shear force basically will be Q into L minus A by 2 minus D. So basically this region, right? This region. Okay. So it is, load is P by L square, and in the vertical direction it is complete L, and in the horizontal direction it is L minus A by 2 minus D, like this region. Okay. So this, so solving this, we get it V equal to P by 2L into L minus A minus 2D. Okay. And that is a load acting. Okay. And gamma CLD is the resistance. Okay. Shear strength of the concrete. Okay. So if we see this, right? So gamma C is basically the this L into the depth. Okay. Depth of footing, and gamma C is the strength of concrete. Okay. So solving this, we get the required diameter, required effective depth of footing to be P into L minus A by P 2 into P plus gamma C L square. Okay. So putting the values. Okay. So we are considering, so that was the total load, so that was the characteristic load. Now taking 1.5 times for finding the factored load or design load, we multiply 1.5 and we get 2550 kilonewton. Okay. L is L, the dimension of footing we took as 3 meter. Okay. Dimension of column is 0.45 meter. Gamma C, the strength of shear strength of concrete is 0.35 newton per millimeter square or 350 kilonewton per meter square, right? So substituting all these values in this equation, basically D equal to P into L minus A by 2 into P plus gamma C L square. So we get the effective depth required is 570 millimeter. Okay. So effective depth of footing required is 570 millimeter. So we got the dimension, the sectional dimension is 3 meter by 3 meter, and effective depth of footing is 570 mm. Okay. So let us check if this dimension is satisfying or not. Okay. So this we got from the one-way shear critical case. Okay. So now let us see for the two-way shear critical case or punching shear case. So in this case, critical section at D by 2 from face of the column, as we discussed. Okay. So perimeter is A plus D into 4, right? Now considering equilibrium of forces. Okay. So this is acting and this is resisting. Okay. So acting is P by L square into L square minus A plus D whole square. So I guess you have understood why it is such, because P by L square is the load acting, right? L square is the total area. Okay. And because it is two-way shear. Okay. It is two-way punching shear. So the load is acting from all the sides. Okay. So there is, it is not like from one direction or two direction, it is acting from all the sides. So just removing this portion, okay, removing this portion, everywhere the load is acting, okay. So that's why it is called as punching shear, okay. So yeah, so therefore this area, removing this area which is a plus d whole square, because it is a square, because column is square, the critical section is also a square. So this area acting will be L square minus a plus d whole square, okay. So therefore the load acting is P by L square into L square minus a plus d whole square, okay. And this is resisting, which is 4 into a plus d into d into gamma p, right, or tau p, okay. So yeah, so uh, that is the that is the punching shear stress, basically allowable punching shear stress, or the shear strength of concrete in punching, okay. So yeah, so putting all these values, this gamma p value is basically taken as 0.25 square root of fck, it is given in IS code, okay. And yeah, so this is square because we have taken it as square column and square footing, right. So this perimeter value comes out to be 4 into a plus d, which is 4 into 0.45 plus 0.57, that is 4.008 meter. And q values p by l square, that is 2550, okay, by 3 square, that is 283.33 kilonewton per meter square, okay. And therefore the shear force which is acting is P by L square into L square minus 8 plus D whole square, which comes to be 2255.21 kilonewton. So this is this value, okay. And if we see our value, that is resisting value, that is 4 into A plus D into D into tau P, right. So that is 4.08, okay. D we got as 570 millimeter, right. So it is 0.57, and tau p is 0.25 root fck. Fck is 220, so 0.25 into root 20. And because yeah, so because this is in this one newton per mm square, so we need to convert it into kilonewton per meter square, so multiplied by 1000. So this value comes to be 2600 kilonewton, okay. That is a resisting value. Acting value is 2255.21 kilonewton, and resisting is 2600 kilonewton. So it is much more than the acting force. So therefore the footing is safe, okay, and the section is okay, okay. So that is so our 570 millimeter depth is okay from one-way shear as well as two-way shear critical section condition, okay. Now let us check it from the depth required from bending point, okay. So from bending moment, so as we just discussed, the mu value comes to be moment at the face of the column, that is a critical section. There the moment comes to be P by L square, or Q into L minus A whole square by 8, and that is, I have broken this down how it is coming, okay. So substituting these values, we get the mu value is 690.89 kilonewton meter, okay. So assuming this as critical section, okay, and from the singly reinforced beam condition, we know that mu is equal to 0.8138 fck bd square, okay. So therefore D is equal to square root mu by 0.138 fck b, okay. So that is the depth of footing, okay, and b is the width of footing. So width is nothing but the L value, okay, because it is a square, okay. So putting the values, we get square root of 690.89 into 10 to the power 6 by 0.138 into 20 into 3000, okay. And solving this, we get the value as 288.86 millimeter. So that is the required depth of footing from the bending point of view. But we have given a value of 570 millimeters, so it is much lesser than the required. The required value is much lesser than the given value, okay. So given value is much higher than the required value, okay. So therefore it is it is safe, okay. The footing is safe and our section is okay, satisfactory, okay. Dimensions are satisfactory. So, so from the three cases, we can say that if we give a footing of sectional dimension 3 meter by 3 meter and depth of footing as 570 millimeter, our section will be safe from all the critical sections, okay, for shear failure, okay. So shear as well as moment failure. So we have designed the concrete section for the footing, okay. So now let us see the amount of steel that will be required, okay. That is a steel reinforcement required for the footing, basically the tensile steel reinforcement. So xu by d value we know that is equal to 1.2 minus 1.44 minus 6.6 mu by fck bd square whole to the power half, right. And mu value is 690.89 kilonewton meter, fck value is 20 megapascal, d value is 570 millimeter, b and l is 3000 millimeter, right. So putting these values, 6.6 mu by fck bd square comes to be 0.2339. Okay, and therefore xu by d value will be 1.2 minus square root of 1.44 minus 0.2339, which comes to be 0.102, right? And therefore the lever arm z value will come to be d into 1 minus 0.416 into xu by d. So substituting the values, we get the value of z as 545.81 millimeters. Okay, so therefore the area of steel, okay, so we can calculate that using the equation mu equal to 0.87 fy ast z. Okay, so 0. Fy value is 415, z value is 545.81, mu value is 690.89, right, into 10 to the power 6, right? So therefore putting the values, we get the area of steel required to be 3506 millimeter square. Okay, so that is the area of steel required. So let us provide 12 numbers of 12 numbers of 20 mm dia bars. Okay, so then the area of steel comes to be 3769 millimeter square, which is more than the required. Okay, so it is okay. Okay, so finally, also we can give a development. We need to find out how much development length we need to give. Okay, so that is mainly for preventing the joint slippage. Okay, so this is the extension of the reinforcement, which is mainly given when there is some joint, say the column is meeting the footing. Okay, so it is given in that case for proper bondage between the steel and concrete in order to prevent any type of joint slippage. Okay, so there is proper bonding. So generally it is found using equating these two equations. Okay, so sigma s is basically the stress in bar due to design load, which is sigma s, and therefore the load will be sigma s into pi by 4 into phi square. Okay, so that is resisted by the bond strength. Okay, so bond strength is tau bd, which is design bond stress, and that is acting in the perimeter. Okay, so it will be uh, perimeter is pi d or pi phi. Okay, and the resistance will be given by the length, that is the development length. Okay, so pi, using this equation, pi phi into ld into tau bt equal to sigma s into pi by 4 into phi square, we get the value of ld as phi into sigma s by 4 tau bt. Okay, so this is as per clause 26.2.1 page 42 is 456 2000. So you can refer this clause also for understanding it. And they have given some certain grade tau bt values for various grades. Okay, for M20 it is 1.2 megapascal, for M25 1.4, M30 1.5, M35 1.7, M40 and above 1.9. Okay, so based on the calculations, we can so based on the calculations we can give the following design. Okay, so yeah, so this is the section which we have to design. So this is the column, this is the footing. So this footing is having a dimension of 3 meter. Okay, and height, the effective depth is 570. Okay, and we assume a clear cover of 50, and because there are two reinforcements. Okay, so if you can maximize this also, you can see here up till here it is 570, and there is both longitudinal as well as transverse reinforcements. So taking both as 20. Okay, so from here this is half of 20, this is 10, and this is 20. So 10 plus 20 is 30, and 30 plus here we have given clear cover 50. So 30 plus 50, that is 80. Okay, so 80 plus the effective depth 570. So 80 plus 570 is how much? 650. Okay, so 650 millimeter is the total depth. Okay, and of the footing. Okay, and this is the your column, and these are the column bars, and this is the development length which has been provided. Okay, mainly in the tension area. Okay, so that is LDT. Okay, and these are the dimensions for the column. Okay, which they have, which we can design. Okay, based on our column designing criteria. So yeah, so and apart from that, as we discussed, the minimum thickness required for footings on soils is 150 mm. Okay, so our case it is 570 mm, so it is much higher than 150. Okay, so yeah, so minimum thickness is 150. So we have provided 650 for the total depth, so it is much higher than 150, and 150 minimum thickness is for footings on soils. Okay, mm in and that is as per the clause 34.1.2 page 64 is 456 2000. Okay, so yeah, so with this we come to the end of the course content discussion. Now let us go for the problem solving. Okay, so yeah, first question is, considering is codal provision, the critical section for bending moment is at A, face of the column, B, effective depth, from the face of the column, C, half the effective depth from the face of the column, or D, none of the above. Okay, A, B, C, or D. So as we have just we have already discussed, the critical section for bending moment is always in the face of the column. Okay, so A is basically the correct option, correct choice. Okay? So hint, as per IS 456, the critical section for bending moment is at the column face. So A, face of the column, is the right option. Okay. Second question, considering IS codal provision, the critical section for one-way shear is at A, face of the column, B, effective depth from the face of the column, C, half the effective depth from the face of the column, or D, none of the above, A, B, C, or D. Okay. So we have just discussed the critical section for one-way shear is always at a distance D, that is effective depth from the face of the column. Okay. So B will be the correct option. Okay. So as per IS 456, the critical section for one-way shear is at effective depth from the face, column face. Okay, so B will be the correct option. So as you can see, B, effective depth from the face of the column, is the correct option. Third question, considering IS codal provision, the critical section for two-way shear is at A, face of the column, B, effective depth from the face of the column, C, half the effective depth from the face of the column, D, none of the above, A, B, C, or D. So we have discussed this also for the critical section for two-way shear. For the two-way shear case, the critical section is at the distance of half the effective depth from the face of the column. Okay, so C will be the correct option. So as per IS 456, the critical section for two-way shear is at half the effective depth from the column face, right? So C, half the effective depth from the face of the column, is the right option. Okay. Fourth question, in design of isolated footing, the minimum percentage of steel HYSD provided should be A, 0.12% of overall cross-sectional area, B, 0.85 by Fy, where Fy is the characteristic strength of reinforcement in Newton per millimeter square, C, 0.8% of overall cross-sectional area, D, 1% of overall cross-sectional area. So which will be the correct this one option. Okay, so here basically we don't give shear reinforcements. Okay, so the minimum reinforcement is same as the design of slabs. Okay, so therefore in design of isolated footing, the minimum percentage of HYSD steel required is how much? 0.12%. Okay, for mild steel it is 0.15%, and for HYSD steel it is 1.12% of overall cross sectional area. So as per IS 456, no shear reinforcement is provided in isolated footing. Therefore, minimum reinforcement is provided as per the minimum reinforcement provided for slab, which for HYSD case is 0.12% of overall cross-sectional area. So A 0.12% of overall cross-sectional area is the correct option. Fifth question, as per IS code, minimum thickness at the edge of the isolated footing should be A, 100 millimeter, B, 150 millimeter, C, 200 millimeter, D, 50 millimeter, A, B, C, D. So as we just discussed, the minimum thickness at the edge of the isolated footing should be 150 millimeter. Okay, so B will be the correct option. So that is as per clause 34.1.2, page 64. According to it, the edge of the isolated footing should be 150 millimeter thick. Okay, so B, 150 mm is the correct option. Okay. Sixth question, a square isolated footing for a square column of size 350 millimeter by 350 millimeter is made to transfer the characteristic load P is equal to 600 kilonewton to the ground. Consider weight of footing as 10% of the characteristic axial load. The safe bearing capacity of soil is 150 kilonewton per meter square. The dimension of the square footing should not be less than A square root 1.1 meter, B square root 2.2 meter, C square root 3.3 meter, or D square root 4.4 meter. Okay, so we need to find the dimension of the square footing. Okay, and this is the column size 350 by 350 millimeter. Load, characteristic load is 600 kilonewton. Weight of footing is 10% of 600, and safe bearing capacity of soil is 150. Okay, kilonewton per meter square. So the characteristic axial load in column is 600 kilonewton, and for footing we have to consider 10% more, that is 1.1 into 600, which becomes 660 kilonewton. Okay, and safe bearing capacity is 150, so it is 150 kilonewton per meter square. Therefore the area of footing which will be required is 660 by 150, right? That is 4.4 meter square. And because we have given a they have given a dimension of square footing, we have to give a dimension of square footing. So the required dimension of square footing is square root of 4.4. Okay, So therefore this D option is correct. Okay? But one thing you have to see here is that uh, here basically they have taken the unfactored load, okay, the actual load that is 660. But while solving, we always need to take 1.5 times, that is the factored load, okay. But if you, in this case, if you take factored load, okay, so it will be higher than 4.4, okay, it will be 1.5 times more, that is it will be 6.6. But there is no square root of 6.6 option, okay. So therefore we have to design for the unfactored load only in this case, okay. So therefore the dimension of square footing is square root of 4.4 meter, okay. So that is D is the correct option, okay. So as you can see, D square root of 4.4 meter is the correct option, okay. Seventh question, find the soil reaction on a square isolated footing of dimension 1500 millimeter by 1500 millimeter following limit state of design made to transfer a characteristic load of 600 kilonewton to the ground. Consider the weight of footing as 10% of the characteristic axial load and the load factor is 1.5. Okay. So, what is the soil reaction on the square isolated footing? Is it A 220 kilonewton per meter square? Is it B 330 kilonewton per meter square? Is it C 440 kilonewton per meter square? Or is it D 550 kilonewton per meter square? Okay. So, which is the correct option? So if you see here, characteristic axial load acting in column is 600 kilonewton, and the footing weight is 10% of this, that is 60 kilonewton. So unfactored load on footing is 660, right? But the design load will be 1.5 times more, as I told you. So it will be, the factored load will be 1.5 times 660, that is 990 kilonewton. And the dimension of isolated square footing is 1.5 meter by 1.5 meter. So the soil reaction due to design load will be 990 by 1.5 square, which is 440 kilonewton per meter square. So as you can see, 440 kilonewton per meter square is given in option C. So therefore C is the correct option. So C 440 kilonewton per meter square is the correct option. Okay. Eighth question. A square isolated footing having dimension 1500 millimeter by 1500 millimeter is made to transfer a characteristic load P equal to 600 kilonewton to the ground through a column of 350 millimeters by 350 millimeters. Consider weight of footing as 10% of the characteristic axial load. The load factor is taken as 1.5. The overall depth of footing is 350 millimeter. The clear cover is 40 millimeter. The diameter of reinforcement provided is 12 millimeter. The one-way shear force due to soil reaction at the critical section for design will be equal to how much? A 119 kilonewton per meter width, B 170 kilonewton per meter width, C 213 kilonewton per meter width, or D 256 kilonewton per meter width. Which is the correct option? Which will be the one-way shear force due to soil reaction at the critical section for design per meter width, right? So here the characteristic axial load in column is 600 kilonewton P. The percentage of axial load considered for weight of footing is 10%, right? Unfactored load on footing is 660, therefore, and the factored or design load on footing is 1.5 into 660, that is 990, right? The given footing size is 1.5 meter, column size is 0.35 meter. The effective depth therefore will be 0.35 minus 0.04 minus half of 0.012, that is 0.304 meter. Okay. So the one-way shear force, okay, due to soil reaction at the critical section V is as per this formula which we discussed in notes in the lecture. So it is P by 2L into L minus A minus 2D, which by solving we get as 178.86 kilonewton. So this is the total one-way shear force. And in the question we have been asked one-way shear force per meter width. Okay. So therefore the one-way shear force due to soil reaction at the critical section per meter width is dividing this by the width, which is basically 1.5. Okay. So dividing this 178.86 kilonewton by 1.5 meter, we get it to be 119.24 kilonewton per meter width. Okay. So this is close to this option A. Okay. So as you can see, A 119 kilonewton per meter width will be the correct option. Ninth question. A square isolated footing having dimension 1500 millimeter by 1500 millimeter is made to transfer a characteristic load P equal to 600 kilonewton to the ground through a column of 350 millimeter by 350 millimeter. Consider weight of footing as 10% of the characteristic axial load. The load factor is taken as 1.5. The overall depth of footing is 350 millimeter. The clear cover is 40 millimeter. The diameter of reinforcement provided is 12 millimeter. The two-way shear force due to soil reaction at the critical section for design will be equal to A 1922 kilonewton, B 1647 kilonewton, C 1073 kilonewton, or D 802 kilonewton, which will be the correct option. Okay. So here, like the last problem, the characteristic axial load given for the column is 600 kilonewton, and the load acting and the weight of footing is 10%, that is 60 kilonewton. So therefore, unfactored load is 660 kilonewton and factored load is 990 kilonewton. And similarly, footing size is 1.5 meter and column size is 0.35 meter and effective depth is 0.304 meter. Now, therefore, here we have been asked the two-way shear force, the total two-way shear force, not per meter width, okay, at the critical section. So that is the two-way shear force due to soil reaction at the critical section. V is equal to P by L square into L square minus A plus D whole square. So that is the formula, right? So substituting the values, we get the answer is 801.8 kilonewton. So that is close to 802, right? So D 802 kilonewton is the right option. So as you can see, D 802 kilonewton is the correct option. 10th question. A square isolated footing having dimension 1500 millimeter by 1500 millimeter is made to transfer uh, a characteristic load P equal to 600 kilonewton to the ground through a column of 350 millimeter by 350 millimeter. Consider weight of footing as 10% of the characteristic axial load. The load factor is taken as 1.5. The overall depth of footing is 350 millimeter. The clear cover is 40 millimeter. The diameter of reinforcement provided is 12 millimeter. The bending moment due to soil reaction computed at the critical section for design will be equal to A 134 kilonewton meter per meter width, B 107 kilonewton meter per meter width, C 81 kilonewton meter per meter width, or D 73 kilonewton meter per meter width. Okay, so which will be the correct bending moment due to the soil reaction computed at the critical section for design per meter width. So in this case, the similar to last few questions. The characteristic axial load in column P is 600 kilonewton. The percentage of axial load considered for weight of footing is 10%. The unfactored load acting on footing therefore is 600 plus 60, that is 660 kilonewton. The design load or factored load is 990 kilonewton, and the footing size is 1.5 meter, column size is 0.35 meter, effective depth is 0.304 meter. Okay. So now the bending moment due to soil reaction, the total bending moment, okay, that will be acting due to soil reaction at the critical section M will be as per this formula, okay, P by L square into L minus A by 2 into half into L minus A by 2, okay. So substituting the values, we get the value to be 109.106 kilonewton meter, okay. So that is a total bending moment, okay. But we have been asked the bending moment per unit width, okay. So width is basically the width of footing, that is 1.5 meter, okay. So therefore the bending moment due to soil reaction at a critical section per meter width will be 109.106 kilonewton meter per divided by 1.5 meter, okay. So that comes out to be 72.738 kilonewton meter per meter width, okay. So this 72.738 kilonewton meter per meter width is close to D 73 kilonewton meter per meter width. So D is the correct option. So as you can see, D 73 kilonewton meter per meter width is the correct option, okay. So with this we come to end of today's class, okay. So next class we will be we will be basically studying the design of staircases, okay. And I think 2 3 classes more will be remaining, right? So yeah, so let us meet next class then. We will study staircase design. So till then, wishing you a happy learning and bye bye.